Let's prepare on bearing capacity of soil. So now we are going to see the topic bearing capacity. So before that, let us see two types of foundation. So one is the shallow foundation and another one is the deep foundation. Okay. So here deep foundation means the depth is greater than the width, and shallow foundation means the depth is equal to width or the depth can be lesser than the width also. Okay. So these two cases are the deep foundation and shallow foundation. So normally in shallow foundation only the rotational bearing failure occurs. Rotational bearing failure normally occurs in the shallow foundation. So the next we are going to see some terms of pressure, bearing capacity and everything. So these are some important terms to be studied in the bearing capacity, but as far I know they have not asked any questions from this in the objective questions. Okay, so let us see that. First one is the gross pressure, which is denoted as Q. So which is the pressure due to all the weight. So it is a general pressure. Okay, so we denote it as Q. The next is the net pressure. So net pressure is nothing but cross pressure minus original overburden pressure. So original overburden pressure is normally we'll be calculating the density into depth. So that is your original overburden pressure. So it is Q minus gamma D. So the next one is the ultimate bearing capacity, which is represented as QU. So it is the minimum gross pressure at the base of the foundation at which the soil fails. Okay, so that is only they have given here, minimum gross pressure at which the soil fails. And then QNU, so it is net ultimate bearing capacity. So it is the minimum net pressure that causes the shear failure. So here we want to minus the overburden pressure from the ultimate bearing capacity. So it is QU minus gamma D. Okay. Then comes the gross safe bearing capacity. So here it is also called a safe bearing capacity. So it is the maximum gross pressure which the soil can carry safely without any shear failure. Okay, so this is the safest bearing capacity. And then the net safe bearing capacity, we term it as QNS, which will be equal to QNU by factor of safety. Okay, so this factor of safety usually we will take it as 3. So this is your QNS. And then QNP, so it is net safe settlement pressure. So it is the maximum net pressure that the soil can carry without exceeding the allowable settlement. So that is only the safe settlement. And then net allowable BC bearing capacity, it is denoted as QNA, so which is the least of these both, QNS and QNP. So among these both, the least can be taken as net allowable. Okay, and then this term is also very important. So as the depth increases, SBC will be increasing only, that is the safe bearing capacity will be increasing only. And then the next is the shear failure types we are going to see now. Okay, so the shear failure types are general shear failure, local shear failure and punching shear failure. So this general shear failure, so here only all the 3 zones of the soil will be getting affected. Okay, so the zones of the soil that and all we will be seeing in the Tessage's theory, which is after this topic. So in that all the total soil will be completely getting the failure. So the soil bulges out. So this normally occurs in the dense sand and the stiff clays. Okay, so this is the maximum failure. And the next lower level is the local shear failure. So here the heaving occurs, and this occurs normally in the medium dense sand. So medium dense sand, they have given a value that is Cu is less than 50 kilonewton per meter square. And the third one is the punching shear failure. Here no changes obtained because the failure surface, no, it does not extend up to the ground level, so we cannot see any failure. So this occurs in the loose sand. Okay, and here are some values to be studied based on the general and local shear failure. So when this occurs means when phi is greater than 36 degree and when strain is less than 5%, and when ID, that is the relative density, is greater than 70% and E is less than 0.58 means GSF, general shear failure, occurs. And the similar case here also, when phi is less than 28 degrees, strain is equal to 10 to 20%, ID is less than 20% and E greater than 0.75, you get local shear failure. And the next is the Rankine's analysis. Okay, so this Rankine's analysis is mainly used to find the minimum depth of the foundation to be used. So they are given the formula D minimum will be equal to Q by gamma into 1 minus sin phi by 1 plus sin phi the whole square. Okay, so here Q is the pressure and gamma is the density of the soil. So here in the code, that is IS 456, they have given your depth of the foundation should be minimum 500 mm. So this is an important point they have asked many times. Okay, and then we have always will be seeing some theories which is used for the studying. Okay, so in the earth pressure, in everything we will be stability of slopes, everything they have used some theories. Similarly in here also for studying the bearing capacity there are many theories. So in that, first let us see, there are many scientists who has worked on this bearing capacity, has given some points about that. So first let us see that and then we will go into detail. Okay, so first one is the Rankine's theory. So it is normally a classical theory which is based on the active and passive. So this active and passive pressure we have already studied in the earth pressure chapter. No, so that is only telling about the Rankine's theory. And then it is Prandtl, so it is for specifically used for clay, and this is a modified version of Terzaghi. Sorry, this was modified by Terzaghi later. Okay, and the third is the Terzaghi's theory, so we will see in detail about that. And then Skempton theory. So Skempton also we have already seen, which have used for finding the pore pressure. Okay, so here they tell that for saturated clay especially this method he has claimed a method. Okay, and then Meyerhof method for inclined load and eccentric load, the safe bearing capacity has been found out by him, and Hansen method, the inclined base, ground and eccentric load he has found. So now let us see about the Terzaghi's theory. So there are some basic assumptions. The foundation is a rough and shallow foundation and it is based on the Moore-Coulomb theory, and then he assumed that general shear failure only occurs there and no shear resistance is present there. Okay, so if this is the foundation means the bottom soil has splitted into three zones. The first zone is the elastic equilibrium zone, and then the radial shear happening zone, and the third zone is the linear shear happening zone. So in the linear shear happening zone, at which the zone is separated means at a failure plane of 45 degree minus 5 by 2. So these are the zones of the soil under the foundation. And then this is the formula for finding the ultimate bearing capacity QU, and the first formula is a general formula and you can tell it for, it is used for strip footing also, but in general we will be always using this formula only for circular and square and rectangle they have given. Okay, so Q is equal to CNC plus 0.5 gamma B N gamma plus gamma D NQ. Okay, so here C is your cohesion value, NC, N gamma, NQ. So these three are dimensionless units. So it is a constant like factors, and other than that gamma is your density, B is your width of the footing and D is the depth of your footing. Okay, so everything you can get from the question itself. And for circular, square and rectangle they have given specifically three formulas. You can go through that also. And then I have told you, this NC, N gamma and NQ, it is bearing capacity factors. It is a dimensionless factor and it is dependent on the angle of repose of soil below the base of the foundation. So this is an important point. So keep remembering that these three factors are dependent on the angle of repose of the soil only and not on any other properties of the soil or not on any other properties of the foundation also. Okay, so based on the phi value only everything is going to be changed here. So as a basic, knowing this is enough, that is phi is equal to 0. So when is phi is equal to 0 in clays? So when phi is equal to 0, it is called as a pure clay. So at that time NC will be equal to 5.7, NQ will be equal to 1 and N gamma will be equal to 0. So now you take the formula of the strip footing. There the formula is given as CNC plus gamma B NQ plus 0.5 gamma B N gamma. Here the N gamma is 0, so the third term goes off, and the second term NQ is 1, so only gamma D will be there, and the first term CNC, so it becomes as 5.7 C. So that is only I have written here 5.7 C plus gamma D. Okay, the next we are going to find QNU. So what is this QNU? It is the net ultimate bearing capacity. We have seen that in the starting, no? So it is nothing but QU minus gamma D. So when you minus gamma D from this QU, you will get 5.7 C alone. So QNS, NS is again, it is the net safe bearing capacity. So for safe bearing capacity, we always divide it by factor of safety. So it is 5.7 C by F. So from this, it is clearly shown that the clay bearing capacity depends only on cohesion. So this is also an important point, and it is independent of the size of the footing. So this is also an important point. Okay, so it does not depend on the properties of the soil and does not depend on the size of the footing, but it depends on the cohesion, and also the factors, the bearing capacity factors depends on the angle of repose of soil. And the next is the in local shear failure, that is when phi is equal to or less than 28 degrees. So we have seen this in the condition, no? Cm will be equal to 2 by 3 C, and tan phi m will be equal to 2 by 3 tan phi. Okay, so in this cases the bearing capacity will be reduced. Okay, so can anybody remember this 2 by 3 already? Because we have studied this already in the earth pressure chapter. If you remember, this means it's a great thing, because in the earth pressure chapter we have studied Coulomb wedge theory, where we have studied the value for del. For smooth walls, del is equal to 5 by 3. For ordinary walls, del is equal to 2 by 3 5, like that and all. In that I will be mentioning that this is called as a Terzaghi value, and I said it is important, and here that 2 by 3 is only used here. Cm will be equal to 2 by 3 C, and tan phi m will be equal to 2 by 3 tan phi. So if you forgot, that means just revise that quickly so that you will be never forgetting that. And then in general, the bearing capacity for strip will be greater than square, and square will be greater than circular. So this is also important. Okay. So now we are going to see the effect of water table, because this effect of water table has some alterations in the bearing capacity formula. So only the gamma will be changing. That is, in the formula we are having CNC plus gamma B NQ plus 0.5 gamma B N gamma, no? So in that, this density factor alone is going to be changed in the formula with respect to the water table. So when the water table is at or above the ground level, means gamma dash has to be used entirely, and if it is the water table is above the base of the footing, so here I have given a diagram. So this is your ground level, and this is the footing diagram I have given. So B is the width of the footing. So when the first case it is at or above the ground level, so this will be a water level, means gamma dash has to be used entirely. In the second case, if it is above the base of the footing, then gamma dash used for 0.5 gamma dash B and gamma, no? So for that factor alone, gamma dash can be changed. And when it is equal or greater than B, equal or greater than B means no correction is necessary. Okay, and then the fourth case is the intermediate position. So that is your ZW1 and ZW2 I have given. So it is an intermediate position. It is in between the depth and breadth. So like that means we have to use this RW1 and RW2 factors. We have to find those factors and then we have to do the correction. So this RW1 is equal to 0.5 into 1 plus ZW1 by D, and RW2 will be equal to 0.5 1 plus ZW2 by B. Okay, so these factors, and these has to be multiplied with the formulas. Where and all we are having gamma, you should multiply this RW1 and RW2 with that formula. Okay, so normally this range of this formula is 0.5 to 1. And then if the water table rises above the ground level in sandy soil, means gamma submergence take place. Okay, submerge of soil takes place. So when submergence take place, which is 50% of the gamma saturation, then automatically there will be 50% reduction also in the bearing capacity. So this is also an important point. And then comes the Skempton theory. So this is the second theory we are going to see in this chapter. So this is used for purely cohesive soils where phi is equal to 0, and then it is dependent on depth and shape of footing. So this is an important point, because in the Tesagi's theory we saw that it is independent of the shape of the footing, but here it is dependent on the depth and shape of the footing. Okay, because in there we termed the NC, NQ, that factors and all with respect to the phi value. No, so but here we are going to determine that factors with respect to the depth and width of the foundation only. Okay, so that only here it is dependent on depth and shape of the footing. Okay, so there are three cases. The case one is at the ground level, the D by B ratio will be 0, and then the case 2 is D by B will be less than 2.5 when it is a shallow foundation, and when it is a deep foundation it is D by B is greater than 2.5. Okay, so these are the three cases. So for these three cases we are going to see the values for strip, square, circular and rectangular. So first let us tell about the strip alone. So here NC we have to use 5.14, and this is the value for the case 2, that is 5 into 1 plus 0.2 D by B, and in the case 3 the NC value will be 7.5. Okay, so these are the values for NC alone. Why I have told this NC alone means, can you find it? Because in the previous theory we saw some formulas, no, that is QU we have found it, no, and at the last point what we got, QU is equal to 5.7 plus gamma D, that is 5.7 C plus gamma D, that is NCC. Okay, so in that case is only used here also, because here phi is equal to 0 is the assumption, so automatically other two terms will be that is the one term will be getting 0, and the next term two terms alone will be there, no, so that two terms alone only considered here also. So knowing about NC is alone enough here. So by knowing this NC you can directly find the bearing capacity by using the formula CNC plus gamma D. So this is alone enough for this method. Okay, so in this CNC plus gamma D we need only NC value, so that we are going to study only NC value for the Skempton's theory. So here in the first strip footing there are three values, 5.14 and 5 into 1 plus 0.2 D by B, and then 7.5. So this is the minimum value and this is the maximum value. So knowing this range is also important. And for the square it is 6.229, for circular 6.229, and for rectangle it is 5 into 1 plus 0.2 B by L to 7.5 into 1 plus 0.2 B by L. And after this Meyerhoff's theory is there, and also we want to learn something about the plate load test, because plate load test is also important, and mostly there will be one question from this plate load test. So we will be seeing that two topics alone in the next lecture as a continuation of this lecture. Okay, thank you and keep watching for the next lecture on plate load test.